So remember last time, what we actually did was we did conditional probability. Okay, let me just, and if you remember also, well, let me say what conditional probability is. As a reminder, if you have two events, A and B, okay, the probability of event B, given that, the probability, excuse me, that event B occurs, given that event A has happened or has occurred, that's represented, so it's really notation by this. So there's just notation for it, probability of B, this vertical bar, then A. And again, this is the probability of B given A. And these are just some other things I said last time. First, it's not commutative in that the probability of B given A may not equal to the probability of A given B. Can that ever happen? I want to say yes, but don't assume that these two are always equal to each other. That's what I'm trying to say. Okay. Now, there was something I misspoke in the definition of independent. I do apologize for that. Well, not really so much the definition, I guess, but something here I wrote last time. For A and B to be independent, you have to have this, the probability of A given B equal to the probability of A given that B complement, which again means that B has not occurred, right? The complement, that's denoted by a little bar up here, right? And remember, the complement occurs, the complement of an event occurs if the event has not occurred. So in other words, the complement of B occurs if B has not occurred. Again, that's just a definition. Okay. And the same thing here. You know, again, B and A are arbitrary, so that's why I'm writing this as well. B, again, is independent from A if the probability of B given A equals the probability of B given the complement of A. In other words, whether one event occurs or not does not affect the probability of the other. So the probability of A is not affected if B occurs or does not occur. Same thing over here. B occurring, the probability of it does not change if A occurs or if A does not occur. Last time I said this was equal to the probability of B and this was equal to the probability of A. That doesn't have to be true. So what I wrote last time was a mistake, and again, I apologize for that. But these equalities are true. And let me say it again. A and B are independent if one of these equations, at least one of these, holds. You know, so in other words, the probability of A, given that B has occurred, is the same, that is, equals the probability of A, given that B has not occurred. In other words, whether B occurs or not does not affect the probability of A. And likewise, the probability of B, that's not going to change if A occurs or if A does not occur. You know, that's the same. That's really what these are saying. That's what I was trying to show last time, and I hope that made sense. So let's move on to an example. So this is actually the example that we did last time. We did not use conditional probability. We are going to use it here, though. Okay? So again, we have a bag of marbles. There's 10 red ones. There's 5 blue and 8 black marbles in there. Again, you can't tell the difference between them except for their color. You know, you can't feel a marble and say, oh, well, this feels like a red one. You know, you can't do that by assumption. So again, what's happening is we're reaching in the bag without looking into the bag. We're choosing a marble at random. We note the color, and then we choose another one. And remember, we're not putting the first one back. So these are just some things here. We're going to show that the events are independent. We're going to determine, that is, if they're independent or not. Okay? And the two events we're going to determine are the event that the first marble we chose is red and the event that the second marble we chose is red. We actually did do this last time, but now we're going to use conditional probability. I mean, last time we argued logically that, well, yeah, they're not going to be independent. Let's show that here as well. So again, we're going to let A now be the event that the first marble is red. Let B be the event the second marble is red. And again, we already know that the probability of B does not change if A occurs or not. In other words, if you did the probability of B given A, right, we last time showed actually that, so we did show this last time actually that this probability is 9 over 22. If I remember correctly, we did show, that was something we did last time. You know, if A occurs, right, that means the first marble was red. Okay, so for the second marble, well, there's one less red marble. There's only 9 now. Moreover, there's only 22 marbles, right, because there's one less marble from the bag. So the probability of B given A is 9 out of 22. And again, if the first event occurred, well, then that means the first marble we chose was a red one. So there's only 9 red then, and thus there's only 22 marbles. So the probability here would be 9 out of 22. Here, what if the first marble was not red? Okay, so let's say we chose a blue or a black one. Well, there's only 22 marbles left because we did choose a marble and we did not put it back, but there are still 10 red ones. So here the probability would be 10 over 22. So in this case, we have this here. So because we have, no, excuse me, we don't, what am I saying? We don't have this, I'm sorry. We don't have this. These are not equal. So the events are not independent. The events are not independent. So again, I'm just reviewing that example. We did see last time as well that if we did put the first marble back, then the events would be independent. We did see that last time. Okay. Remember, we also talked about the probability of events A and B occurring, right? You know, in other words, we wanted to find the probability of 2 events occurring. Well, if they're independent, it's actually easy. You just multiply their probabilities. If they're dependent, though, then you're going to have to use conditional probability. Namely, if you have 2 events, A and B, the probability of A and B occurring at the same time, if they're dependent, it's the probability of A, right, times the probability of B given A. So it's the probability of A times the probability of B given A. You could also calculate, I mean, really A and B are arbitrary, but you could also think of it this way. It's the probability of B times the probability of A given B. Either one. Either one. Again, we're assuming these events are not independent. They're dependent. So that's how we calculate the probability of A and B occurring. And now that's really cool. That's really nice because now, going back to the previous example, we can actually determine the probability of both events A and B occurring. In other words, we can determine the probability that the first marble is red and the second marble is also red. We can get that probability. We already calculated these, right? You know, the first marble, right? There's 10 red marbles in there. So the probability of A is 10 out of 23. And the probability of B given that A has a given A, meaning the probability of that the second marble, excuse me, is red, given that the first marble was red, that's 9 out of 22. So using the previous slide, the probability of A and B occurring is this product. which if you multiply these, you get 90 over 506. 90 over 506. I mean, you could, if you want, convert that to a decimal. I would just leave it as a fraction like that. Okay. Are there any questions about this? Okay. This one I want everyone to take about 5 minutes to try. Here we have a standard deck of 52 cards. Okay. And basically what's happening here is that we're choosing a card at random and then choosing a second one. Notice we're not putting the first card back. So I want everyone to try these out for about 4 or 5 minutes. You're going to find all these probabilities. Then we'll go through it together. Okay, so let me stop the recording. So you'll do that together.